Warning, kids, don't be fooled by internet math propaganda. This sheet of equations is a piece that regularly makes the rounds online. Look at how beautiful numbers are. Shiver in ecstasy. There's nothing special at all about this, though. It looks cute and fun, but if you've ever heard of factoring before, then the magic will leave like a fart in the wind. Just look at this equation, row 1, column 2. Everything here is just begging for us to factor out a 2. In the numerator, we get 2 times 111, and in the denominator, we get 2 times 1 plus 1 plus 1. Now the 2's cancel out, and what are we left with? Well, of course, it's the first equation. Of course, this first equation is written in a funny way, but it's just 111 over 3, which happens to equal 37, just like all of the other expressions on this sheet. And isn't that what the kids are saying these days? 37! 37! Well, anyways, the factoring we just did can be repeated on all of these equations. Take out the 6's, it's 111 over 3. Take out the 7's, it's 111 over 3. At the end of the day, it's all 111 over 3, and yes, it always was. So the trick, if we are to call it that, is just noticing that if we multiply 111 by some number, say n, then the product is just a few n's right next to each other. That looks kind of fun. And if we multiply 3 by n, we get 3 copies of n, which can be written as n plus n plus n. Now, what was once 37 is just a bunch of n's. Then we just take our discovery to the internet to show that we do know math and we're smart enough to appreciate its unparalleled beauty. Again, the trick, or what makes this look like an interesting observation, is that the number 111 over 3 happens to look quite striking if you multiply the numerator and denominator by some number from 1 through 9 and write it a certain way. Of course, if you multiply by 10, then the effect is lost. That doesn't look so special, and that's why the propaganda only goes from 1 through 9. But the premise here is so simple that it's not difficult to make some simple modifications to get some other cute sets of equations. Of course, 111 times 3 is 333. But if we change it to 112, we can also get something that looks kind of striking. 112 times 3, well, that would be 333. That's 111 copies of 3. Plus that one extra 112th copy. Hey, it's just a bunch of 3s. This almost looks like it could lead to a substantial math fact. Now, in the previous trick, we had 111 divided by 3, but we can't do that with 112 because 112 divided by 3 is not a whole number, so it's not going to look super impressive. However, 112 is divisible by 4, so our key number is going to be 112 divided by 4, which, if you're curious, is equal to 28. But of course, we're not going to get a million impressions on X if we write it like this, so we're not gonna. Instead, we're going to write 112 as 111 plus 1, and how are we going to write 4? That's right, 1 plus 1 plus 1 plus 1. Now we just multiply the top and bottom by a number from 2 through 9, and we get another cheap trick. Of course, at the end of the day, it's just the fact that we've written an expression with all of these 1s that makes the multiplication leave an impression. Instead of using 111 plus 1, we just as well could have used 111 minus 1 to get another cheap trick. Then the denominator could be 2, 1 plus 1, or 5, 1 plus 1 plus 1 plus 1 plus 1, just so that everything's equal to a whole number. Though really, if we wanted to be super lazy, we wouldn't even have to do that. We could just leave the denominator as 1 plus 1 plus 1 plus 1 and not invoke the result of the division in our representation of our incredible math fact. So instead of writing out all the equations saying, hey look, they're all equal to 37, isn't that beautiful? I could just write out all of the expressions, not write what they're equal to, so I don't have to even worry about if it's a whole number or not. Say that all of these are equal and that you should... A wise man once said, the Browns is the Browns. He was talking about a football team, but we could say the same thing about numbers. 3 is 3. doesn't matter if you write it as 1 plus 1 plus 1, or 4 plus 4 plus 4 over 4, round 3, or handsome 3. How we express it doesn't change what it is. And that's just another way we know that this is a cheap piece of math propaganda. It's a type of fact that we call base dependent. All these numbers are written in our familiar base 10 system. 111, for example. It's 100, or 1 copy of 10 to the power of 2, plus 110, or 1 copy of 10 to the power of 1, plus 1 unit, or 1 copy of 10 to the power of 0. If we wanted to use a different base, and say write 111 in the base 5, or quintic system, then the number 111 would look like this. That's 4 copies of 25, or 5 squared, plus 2 copies of 5, or 5 to the 1, plus 1 unit, 1 copy of 5 to the 0. And 421 over 111 doesn't look too worth shivering in ecstasy for, does it? Here's how the rest of the so-called beautiful equations fall from their spurious pedestals at the face of the quintic spell. So understand, all of these numbers are in base 5. The 9th one, for example, here in the denominator you see what looks like 14, but that's not what it is. This 1 is 1 copy of 5 to the 1, plus 4 copies of 5 to the 0. That's 5 plus 4, that's 9 plus 9 plus 9. It seems natural that we should disregard properties of a number that depend on the way we choose to write it, since this shows the property isn't innate and held by the number, but held by the representation, which is a bit arbitrary. While these properties don't enter into serious mathematics, they can be fun and are a beloved part of what's called recreational mathematics. I don't know who you are that clicked on this video, but I do know that someone who finds this as a good example of the beauty of numbers probably doesn't spend too much time doing math. There's no shame in that. I mean, I, for example, don't spend much time researching 20th century horses, relatively speaking. But you might think, wow, what a trick this piece of propaganda was. Turns out math isn't just useless, it's also not beautiful at all. Well, I figured we should finish with something a little bit fun to make you say, okay math, I see you, I see you. Here's a question. How many kilometers are 89 miles? You might know the conversion factor offhand, but if not, keep watching for a pro trick. Math people love things called sequences. They're ordered lists of numbers that are usually infinite. One famous sequence is 97, 99, 01, 08, 13, and the next term of the sequence was once thought to be 25, but currently the rock stars of the math world are trying to prove the next term is in fact 26. We'll see. Another famous sequence you might have heard of is the Fibonacci sequence. It looks like this. We could explain the sequence using the population of immortal breeding rabbits, but I suppose it's simpler to say that the first 2 terms are 1, and then subsequent terms are found by adding the previous 2. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. You can see the pattern. We've written up to 144. We could add these 2 numbers to get the next term if we wanted, and continue as far as we like. Now, something curious happens if you divide consecutive terms in this sequence. It's a little wonky right at the start, but if we skip to say 3 over 2, that's equal to 1.5. The ratio of the next pair of consecutive terms is 5 over 3, which is about 1.67. The next ratio would be 8 over 5, which is 1.6. The next one, 13 divided by 8, is 1.625. It kind of seems like these ratios are approaching something, and indeed they are. They're approaching the celebrated number called the golden ratio, written with the Greek letter phi. Its exact value is 1 plus the square root of 5 all over 2. And it's approximately 1.618. And you can see how we were getting close to that ratio as we went further in the sequence. 55 over 34, just as one more example, is about 1.618. Now, back to our question. 1 mile is about 1.61 kilometers. And wow, those two ratios, 1.61 to 1 and the golden ratio, 1.618, are pretty darn close. And this means that we can use the Fibonacci sequence to approximate conversions between miles and kilometers, because the Fibonacci sequence grows approximately in this ratio. When describing equal distances, kilometers will be greater than miles. So to convert from miles to kilometers, we have to go up the Fibonacci sequence. For example, to go from 89 miles to kilometers, look at the Fibonacci sequence. Here's 89. Just go to the next term to convert to kilometers. The terms grow approximately by the mile to kilometer conversion factor, so 144 is a pretty good approximation of 89 miles in kilometers. A more exact answer to this question is 143 kilometers, but you can see our answer of 144 from the Fibonacci sequence is pretty darn close. Of course, if we had 144 kilometers and wanted to convert to miles, we could just go down the Fibonacci sequence and see that it's 89 miles approximately. Of course, going backwards works because in that case we're pretty much dividing by 1.61, which is how we convert kilometers to miles. Now, if the number you're trying to convert isn't a member of the Fibonacci sequence, you'll have to do some rougher approximations, but it's still a cute trick. For example, if we wanted to convert 40 kilometers to miles, the closest we can get to 40 in the Fibonacci sequence is 34. So to convert to miles, we step back in the sequence to get 21 miles. Now, we know this will be an underestimate since 34 is less than 40, so we might just call it 25 to account for that underestimate. So with the Fibonacci sequence, we'd approximate it's 25 miles. In truth, 40 kilometers is about 24.8 miles. Again, that's pretty good. Of course, you could just remember the 1.61 conversion factor and do the mental multiplication or division, but I think an average math person is more likely to know the first handful of terms of the Fibonacci sequence offhand than they are to know that conversion factor. And of course, you don't need to know the terms offhand, you just need to know how they are defined and you can calculate them. Anyways, don't be fooled by dirty online math propaganda. Numbers are beautiful, but these equations aren't really any evidence of that. If you want evidence of that, look no further